polar graphs is just like studying rectangular graphs. Depending on their form, their graph can look different. So like we know about linear graphs, quadratics, rational functions, polynomials, they all have different characteristics and things that happen because of the function. The same is true for the polar graphs. We're actually only going to be graphing 3 of the special types of polar graphs. Today we're going to do 2 of them, circles and rose curves. Tomorrow we're going to do the Limaçon, French. And there are some other polar graphs. There are spirals and lemniscates and other things, but we'll only do 3 of them. So there's 3 equations, 3 versions of a circle. You should write these down in your notebook. R equals A times cosine theta, and R equals A times sine theta. We've actually already looked at this R equals A. On Thursday when we were converting rectangular and polar, we had an equation that looked like, I think it was R equals 2. And I said, if I don't give you like an ordered pair with an R and a theta, if I just tell you that R is always 2, what are you going to end up graphing? And we decided we'd be graphing a circle, because we'd go out to the second ring, and we just kind of go around for all the angles, because we don't know what angle, so we'd end up drawing a circle. So let's draw an image like we would see. So, oops. Back up. Draw an image like this. Your pole is right there at the center, so remember your pole is kind of like your origin. And these are always circles that have a center at the pole. So the center is at 0, 0. And if you think about this value of A, remember it's like we'd go out to the second ring, so that A actually represents your radius. So if I saw R equals 5, I would know it had a center at 0, 0 with a radius of 5. I'm going out to the 5th ring. Simple as that. If you did any of the graphing activity, you would have discovered A cosine theta and A sine theta do not work the same way. So I actually have my graphing calculator loaded, so I'm going to pull up my graphing calculator. First thing, if you haven't done your graphing discovery activity yet, you'd have to go into your mode and you got to change a few things. It's at the top of the yellow sheet, so you need to like follow these directions first. You need to be in radian mode, and you also have to change it into polar mode. So that when you want to start graphing in polar mode, you still hit the Y equals menu, but you're going to notice a change depending on which mode you're in. When you're in polar mode, instead of all those lines saying Y equals, now they say R equals, which that should make sense to you, because when we write equations in polar form, we try to make R all by itself, right? And I don't care if you're typing things in or not, but you can always do it on your own, and it's valuable. So I'm just going to type in 8 cosine theta. And when you want to get your variable theta, you just hit that same variable button next to the alpha, x comma t comma theta comma n. Depending on what mode you're in, it will bring up the appropriate variable. So if you're getting x's and y's, you're not yet in polar mode. So I typed in 8 cosine theta. I'm going to go ahead. If you haven't already, you need to do zoom 6. That'll like recenter. Oh, I got to unhighlight. You got to recenter your graph, so you do zoom 6 standard. That recenters it. But notice that doesn't really look circular. That's because it's showing up on a rectangular screen, so it can't be 1-to-1 ratio if I'm doing like -10 to 10 both ways. So then if you do zoom 5, that will square it out, and now it looks circular. But that's all up in the directions on the yellow sheet. Okay, so this was 8 cosine theta. Where do you see the number 8 in the circle? It now represents the diameter. The A value for the cosine graph is the diameter of the circle, not the radius of the circle. Where is the center of this circle at? For 0, halfway across, right? And then 0 up or down. If I go into y equals, I'll change this to be 5 cosine theta. Okay, that confirms it, right? Now my diameter is 5. My center must be at 2.50. Okay. If I go into y equals, this is like what your graphing activity is all about. You just plugging in numbers. I'm going to put a negative in front of it. Notice what happened to my circle. It moved over. Okay. Now there was a question on the graphing discovery activity, like could you build a snowman? And the correct answer to that should have been no. Meaning, like, could you have like 3 body parts of a snowman on top of each other? No, because if you try putting plus or minuses, like vertical shifts and things, it doesn't work. They don't move off of the pole. That makes sense because it's a polar graph, so we got to be connected to the pole. So we can move it side to side by putting a negative there, but we can't move it up and down or left and right. If you want to see the sine graph, so I'm going to go over here. I'm going to highlight my sine. So this one's going to show up in red. So I got 2 sine theta right now. I'm just going to go ahead and hit graph. Notice what's different about the sine circle. Instead of opening around the x-axis, it's opening around the y or vertical axis. So it's opening up. And then if I were to put a negative in front of that one, and hit graph, then it would flip it down. So I can get up, down, left, right, based on which trig function I use. So we're going to write these things down. An A cosine theta graph will start on the horizontal axis. Will always be symmetric to the horizontal axis. The r equals a sine theta will always start at the pole and will be symmetric to your vertical axis. Always. Okay, in the drawing, we could label that the diameter is now A for each of these. So what would that mean about your radius? It would be half of A. Yeah. So we could say the radius is A over 2. Like we were able to say where our center point was when we had like an 8 in for A was at 4, 0. So we could say something like here our center is at A over 2, 0. And then flip flop those if it has vertical symmetry. Now remember, if there's a negative A out front, then your circle shows up on the other side, and so move your center will be negative for both of those. Okay, now you're going to be asked about how many zeros a graph will have in polar graphs. So that's where these two statements starts on the horizontal axis and starts at the pole, become really important. Like right now, like what does it matter where it starts? Well, it matters where it starts when you start counting zeros. Back with rectangular functions that had x and y in them, when I would ask you to find zeros, like in a polynomial function, you were finding all of its x-intercepts. You would say y equals 0, and all the x values which go left and right, and those represent x-intercepts in the graph. Well, polar is something different. If you set r equal to 0 and solve for all of the angles where that happens, you're going to find places that are just at the pole. That's where you are when r equals 0. You don't move off of the center point because you have no radius. Okay. Now, it's hard to see how many zeros you have unless you know where your graph actually starts. So I'm going to look at this a cosine theta. It always starts out on the horizontal axis. So if it's positive, it always starts over here on the right. If it was a negative graph, it would start over there on the left. So it's starting at the horizontal axis, not at the pole. If I want to sketch this circle, count how many times I cross the pole. 1. That's it, right? So the number of zeros here is 1. The sine graph starts at the pole. So that starting point counts as a 0. So I have 1. To draw the rest of the circle, I got to end back at that point, so that counts as 2. So this one has 2 zeros. It has an extra 0 because it starts and stops at the pole twice. The cosine only passes through the pole one time because it starts out on the horizontal axis. How many zeros do you have for r equals a? None. Yeah, Brian is saying 0. Number of zeros, 0. The x-intercepts are no longer what we consider zeros. We're looking for points at the pole, but that has a center at the pole. None of the points on the circle are at the pole. Okay. Let's graph a circle. Now you will get a homework assignment that is a worksheet, so you won't have to like copy all this down every time. Okay. If I were putting this in my notes right now, I would do like a simpler version where maybe I just do the vertical and horizontal axis, and you can put in the other lines if you want. And we're going to graph r equals -5 sine theta. We're going to be asked the same like set characteristics for the circle and the rose curve. Tomorrow when we do the limaçon, it'll ask some different questions, maybe less questions, I think. Well, right now, we're pretty much under the assumption that this is a circle. When I talk about the rose curve and its equation, we'll look at like how can we tell the difference between the circle and the rose curve. But for right now, we say it's a circle. If you've done the graphing activity and you've like looked for patterns on your own, you already kind of know some things about this circle. Because it's sine, you know it has vertical symmetry. And because it's negative, you know that it like goes below the horizontal axis. Kind of already know that. To get the max r value, just take the absolute value of your a, whatever's in front of your sine or cosine. So what would be our max r value here? 5. How many zeros does an A sine theta circle have? 2. Sine starts and ends at the pole. Those count as 2 zeros. So that's just something like that you need to know. And we'll see some kind of pattern with the rose curves. It's not the same, but it'll be the same-ish. Okay, now if you tell me there are 2 zeros, then on the next line, when you list the zeros, you should have that many zeros. So I'm saying they should match and that you should have as many zeros listed as you told me. Don't list 3 if you tell me 2. Don't list 1 if you tell me 2. There should be 2 of them. Okay, to find these zeros, we're going to do like we would normally do with any function in rectangular form. When we wanted to find zeros in rectangular form, we would set y equal to 0 and solve for x. So to find zeros in polar form, we're going to set r equal to 0 and solve for theta. So here's where we get our zeros. Well, divide both sides by -5. 0 equals sine theta. We usually start like our lowest angle value here is going to be 0. And then we like just go around as many times as we need to get the number of zeros. So what's the first 0 you know that has a sine of theta? Pi halves has a sine of 1 because you're going up 1. 0 has a sine of 0 because you go right 1, up or down nothing. So its sine value is 0. So 0 is a solution. What's the next angle that has a sine of 0? Pi. Now that I have the number of zeros I said on the line before, I just copy down my zeros. 0 and pi. Now, I'm going to use those zeros to help me build my significant points, which is basically like a table of values to help you graph. Since both of these are zeros, these are the angles, right? Theta equals 0 and theta equals pi. Since they are by definition 0, their r value is 0. Okay, so I could put 0 and pi in here. I'm going to leave some space in between. But both of them give me r values of 0 because I said they were zeros. I'll move it up. Okay. Well, plotting those 2 points that are zeros is not really helpful in a polar graph because all the zeros happen at the pole. So you're just plotting 0, 0, and then 0, pi on top of each other, and you can't really draw a graph with that, right? So we're going to see this. A really good point to have is exactly in between 2 zeros. It'll give you your max R value or the opposite of your max R value. So what's exactly in between 0 and pi? Pi halves. To figure out what R is at pi halves, I have to plug it back into the original equation. R equals -5 times the sine of pi halves. The sine of pi halves is 1. -5 times 1 is -5. So you're just plugging it in like a table of values. It just helps you pick a theta if you pick the one right in between 2 zeros. I'm going to write this one down below this one time. Think about from Thursday how you plot the polar coordinate -5 pi over 2. Since the r is negative, it means don't go in the direction of pi halves, go in the opposite direction. So rather than counting up 5, we're going to count down 5. So 1, 2, 3, 4, 5. This point right here is -5 pi halves. And what that does for me is it gives me 2 endpoints on my diameter. 0, 0, and that polar coordinate, -5 pi halves. So now I know where my circle is. I just draw a round shape. I just keep saying to myself, round, while I draw round, 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 circle. If you don't say round, you might not get circle. Round, round, round. Round. Everything is round. Okay, now, look at that graph. It confirms what I had originally thought about negative 5 sine theta, that it would be symmetric to the vertical axis, so it has vertical symmetry, and that it would go down, and that its diameter would be 5. Everything corresponds. Okay, does anybody have any questions? If it was a cosine theta, what's the first angle when cosine is equal to 0? Pi halves, because you go 0 left to right and 1 up, so its cosine value is 0. And a cosine circle will only have 1, 0, so you would say 1, 0, and on the next line, your 0 would be at pi halves. When you're trying to create your table down at the bottom, it would probably be helpful if you put pi halves, and then like the next one where the cosine is 0 is 3 pi halves, so the one in between is going to be pi, but I think you can also just reason through that to help you out. But you only need to list 1 on that one. Okay, any questions before we do the rose curve? Okay, rose curves it is. These are the 2 equations for a rose curve. As you are jotting them down, how will you be able to tell the difference in an equation if it's a rose curve or if it's a circle? Dylan says, if it has something multiplied by theta. So in the circle, what was in front of theta? 1. Okay, so if you have a 1 in front of theta, it's a circle. If you have some other integer in front of theta, 2, 3, 4, 5, 6, it's a rose curve. Could be 7, could be 20, could be 100. If you have a fraction, it is not a rose curve. Some other shape. You can put it in your calculator if you want to see what it is. We did it in third hour. But it's just like saying like, okay, if you do x squared, it's a quadratic, but if you had like x to the 5 halves, that's not a parabola anymore. So it's like something different. And we're not going to graph it. Okay. I'm going to go to my calculator. I'm going to do some rose curve investigation real fast. Let's see, go to my y equals. I'm going to shut off my circles. Okay, I'm going to start with 7 cosine 2. So I'm going to start like, circle would be 1. So the next integer that I could plug in would be 2. And I'm going to graph that. It's going to show up in black. Okay, my A was 7, my N was 2. Can you see either of those numbers in my rose curve? Which number can you see pretty easily? 7. 7 represents the length of the petal. Okay. So 7 is the length of the petal. I have how many petals? 4. Okay, let me change N. So instead of 2 theta, I'm going to do 3 theta. Petal length is still 7, but now how many petals do I have? 3. Okay. I'm going to go down and I'm going to change it to 4. Petal length is still 7. How many petals do I have? 8. Anybody want to take a guess when we change it to 5, how many petals there will be? 5 petals. How many petals when N is 6? 12. When N is 7? 7. So there's 2 rules. If N is odd or if N is even. Yeah, you could get some really cool pictures if you make N equal to, 20 or something like that, then it has 40 petals. If I do a sine graph, So I'll do 3 sine, and I'll also do a 5. So now they have the same end, but they have different A's. You know, you can see the difference, obviously, between the length of the petal. So the petal is shorter on my sine graph because I put a 3 instead of a 7 out front. And then even though they both have n equals 5, so they both have 5 petals, notice that their petal locations are different, and that's due to like the values of sine and cosine as you evaluate. Okay. So there's some different rotational pieces there. Do you also notice how like in each of the rose curves, like the petals are evenly spaced around? Okay, so there's like rotational symmetry in your rose curves. Okay, so let's talk about these rose curves. Things that they have in common. Okay, so this goes for both of them. If n is odd, there are n petals. If n is even, there are 2 n petals. And this is my public service announcement over here on the side. There's 2 ways to spell what sounds like petal, right? I mean to say it with a T. I think it actually sounds like a D when I say it. Okay, but petals are with flowers, and petals are on bikes or your gas pedal. Okay, rose curves don't have petals.
Unless they're riding their bike.
They don't have bikes. For each of them, A is still responsible for the length of the petal. And then, you know, we're going to create a significant points table of values, again, to help us graph. But we're actually only going to do it for 1 petal. Because, like, if I give you a rose curve with 8 petals, you don't want to have to plug in that many points. So when I'm graphing, I'll use my significant points to get the location of 1 petal in the right spot. And then I'll use something I call petal spacing. So this goes off of the idea that the petals are evenly spaced around the rose curve. You have 1 rotation that is 2 pi or 360, and you're going to divide it by the number of petals that you have. So I say 2 pi divided by the number of petals. And those are their similarities. There are some differences. So I have some differences below each of the equations. Well, you should see some similarities between like how the circles work and how the rose curves work. So remember the A cosine theta circle had horizontal symmetry and started on the horizontal axis. So that still holds true for A cosine and theta rose curves. And then if it's a sine, it will have vertical symmetry always, and it will always start and end at the pole. So that sine means it's going to have an extra 0. Yeah, because it's going to start and end at the same spot. Okay. In terms of numbers of zeros, I'm going to draw a rose curve with 4 petals that follows the cosine rule. So it would start on the horizontal axis. It could start right or left depending on if it's positive or negative. And as I draw my petals, think about how many times I'm going to cross my pole. Okay. There's 1, 2, 3, 4, and when I close that, I don't cross again, right? So I had 4 petals, and I had 4 zeros. So the number of zeros equals the number of petals. if we think about, instead of starting out on the horizontal axis, if you start at the pole, then to close your shape, you have to end at the pole. So you're going to get an extra 0. It's going to be the number of petals plus 1. Which, again, is really the same rule for the circle, right? The cosine had 1 0, but the sine had plus 1 more because it starts and stops in the pole. And if you want to see that one, I can draw a rose curve that has 4 petals. So I would start at the pole. So there's 1, 2, 3, 4, 5. So I do have 5 zeros. Okay, so we're going to do a graph of a rose curve. We're going to graph r equals 4 sine 2 theta. And notice it's got all the same characteristics that we did for the circle. So shape, max R value, number of zeros, what are the zeros, make a list of significant points, and graph it. Okay, when you look at this equation, how will you know if it's a circle or a rose curve? If theta is multiplied by something other than 1. So this must be a rose curve. Now, when you say what shape it is, I'd like for you to say it's a rose curve with how many petals? So if n is equal to 2, that's even. And if n is even, there are 2 times n petals. So we could say it's a rose curve with 4 petals. And that just sort of holds you accountable to like how many petals you end up drawing in the picture, right? So it's good for you to think about with the shape. Okay, what's your max R value? 4. Absolute value of A again. Number of zeros, if it is 4 sine 2 theta, it has 4 petals, so it could be 4 or 5. This one has 5. Sine always has 1 more because it starts and ends at the pole, so it's got an extra one. Now, if you say that it has 5 zeros, remember on the next line when I ask for the zeros, they have to match. So I'll go have 5 angles listed right there. To find those 5 angles, I go back to my equation, set R equal to 0, divide by 4. You can use a little knowledge from chapter 5 about solving trig equations. We can't divide by this 2 until the very end, so we say 2 theta equals. And now we start listing 5 angles that have signs of 0. Well, we already know the first 2, right? So we use them on our circle. 0 and pi. But I need 5, so I gotta keep going. What's the next one? 0, pi, 2 pi, 3 pi, 4 pi. I need 5 zeros. So I have to just keep going around that circle until I get all 5. Oh, sorry. I'm thinking about 5 zeros. Thank you, Hannah. Are those the angles that I write on the line? No, because I still have to divide by 2. So divide by 2. So the zeros are 0, pi halves, pi, 3 pi halves, and 2 pi. Okay, now in the significant points, this I'm going to do a little bit like similar to the circle. I'm just not going to do all those points because that's a lot to do in a table of values. So we're just going to make one petal. Okay. To make one petal, you can pick any 2 zeros, but I always pick the first 2 zeros. So I'm going to put 0 and pi halves in. Put whatever's exactly in between them, which Dylan is saying is pi fourths. Okay. These, of course, give me zeros. I'd have to plug this in. R equals, what is it? 4 times sine of 2 times pi fourths. So that's 4 times sine of pi halves, which is 1. So that's 4 times 1, which is 4. So I'm plugging that back into the original equation, 4 times sine 2 theta. And what that tells me is when I go to pi fourths, go forward 4. That's a petal. So I've got my points at the pole, and then at pi fourths I would go 1, 2, 3, 4 out. That's the end of a petal, so it has length 4. Draw my petal. Now, I really don't want to do that for 3 more petals, so I just go ahead and use my petal spacing. Take 2 pi, divide by how many petals you have, so your spacing you could think of as 2 pi fourths, or you could think about it as pi halves. Either one is fine. If you're having trouble, go to the angle that you know, pi fourths, and add your spacing. Your next petal will be at 3 pi fourths. And your next petal will be at 3 pi fourths plus 2 pi fourths, 5 pi fourths. And then add 2 pi fourths again, and it'll be at 7 pi fourths. Okay. Now I'm going to make an error on this. I missed it. But can you see that, like, if you take a step back on your quiz, you look at it, can you tell that petal is wrong? Yeah, it doesn't look evenly spaced. I'm going to get some petals that have long spaces in between 2 of them and short ones in between others. But you know something isn't right. So use your eyeballs and say, does that look evenly spaced? Yeah, that looks better. Anything new with us? Dylan's going to come around and pass out your homework. Thank you, Dylan. I'm going to pass back your quizzes.